When I sent Andrea this vague title a few months ago, I had in mind some work we've been doing in epsilon near zero materials and flat bands for augmented reality, and a few other projects. But ultimately, I decided that I thought it would be interesting to try to give a 45-minute talk about just focusing waves, both in free space and in complex media. Now, this is a challenging talk to give for two reasons. First, we have the world experts on focusing in complex media in this collaboration, Professor Emmanuel Fort and Professor Matthias Fink, and there are many other here who have done pioneering work there. But that's not a challenge. I view that more as an opportunity. This is the best audience to present this work to. Perhaps the more serious challenge is that when you talk about focusing in free space, as you can see in these visuals, it's not clear if there are any interesting questions since the time when journals published in black and white. And so I'll try to convince you, at least if there aren't new questions, there are interesting subtleties, and I'll use that as a foundation for then talking about complex media. So you are required by law, talking about focusing in free space, to talk about the diffraction limit. The typical Airy pattern that gets formed is the Bessel function divided by its argument. I won't explain this much more, except to say that the way the usual discussion of the Airy pattern works is you say, if I have a circular aperture and I shine light on it, what pattern is produced? But when we talk about limits, we should be talking about the answer to some kind of optimization problem. So is there an optimization problem that the Airy pattern is the extremal solution for, the optimal solution? And that might be, I have an aperture and I have a metasurface I can put in the aperture. And over all possible metasurfaces, should I, in some scenario, produce the Airy pattern? So this type of question is going to decorate my whole talk. And so let me step away from this for a second and just review a couple simple techniques that will form the basis for 80% of the results in the talk. The first one is that there are many optimization problems that you can write as maximizations of quadratic forms. The inner product of a vector with a matrix with a vector, and maybe there's a condition, something like the norm of the vector is 1. Famously, the Rayleigh quotient says that that maximization produces an optimal value given by the largest eigenvalue of that matrix, and the optimal vector is the corresponding eigenvector. When that matrix is rank 1, the solution is even simpler. When A is rank 1, you can write it as an outer product of a vector with itself. And in that case, the eigenvalue can write down directly as the squared norm of that vector, and the optimal x in this case is just the normalized version of that vector. Technically, rank 1 could also have negative values here, but then the maximum would have just a trivial 0. So we'll exclude that case. In all cases, it's going to be these positive definite rank 1 matrices. The last bit of mathematics, if I want to project into some basis, if I have some orthogonal set of vectors, x sub I, the well-known projector is the sum of outer products of these xi's. We use this all the time in quantum mechanics and resolution of the identity and things like this. What's maybe less well-known, but certainly a long-standing result, is that if I have an arbitrary collection of vectors that may not be orthogonal or normalized, I can just put those vectors as columns of a matrix A. I can take the outer product, A dagger, a lot like these outer products here, but I sandwich in between the inverse of A dagger A, and that actually essentially effectively ortho-normalizes the whole basis and projects into the basis as well. Then one more physics idea is the classic equivalence principle. If I have electromagnetic fields everywhere in space, E and H, I can draw a bounding surface. On that surface, I can put electric and magnetic currents, and they create a discontinuity in the fields. And so if I adjust those currents correctly, I can null out the fields, the exterior of the surface, just by selecting the electric and magnetic currents appropriately. And this goes back probably 100 years. OK, so what problem does the Airy pattern maximize? There are a few different problems one can give. I will focus on one, which is that if you have access to just propagating plane waves over some numerical aperture, NA, and you say that you're in some paraxial limit where the numerical aperture is small, and you ask, if I focus light at a point on a plane in the distance, what is the field that maximizes the intensity at that point? So the answer to that question is ultimately the Airy pattern. It's very simple to see this using the tools I just described. If we write the electric field as a superposition of some coefficients of wave number k against plane waves, then what you want to do is maximize the squared field at the origin such that the total energy in the plane waves might be 1. What does this have to do with Rayleigh quotients and rank 1 optimizations? The electric field at the origin is just the integral of the coefficients against the plane waves, but at x equals 0, that's just 1. And so that's just the inner product of the coefficient vector with a vector that's essentially the identity. And so if you want to imagine this in some discretized space with v and c being discrete vectors, it's a vector of 1 taking the inner product of that with the vector of coefficients. Because E of 0 is just a scalar, and so it has to be some vector inner product with c. And so then the square of the electric field intensity at the origin can simply be written as the square of that inner product, c dagger v, v dagger c. This is a rank 1 Rayleigh quotient problem. The optimal coefficients are just the v's, just 1s. You should excite every plane wave with equal amplitude. You can then do all the integrals for what field that produces. It's exactly the classic Airy pattern. You get the classic results. The full width half max is half a wavelength. The first 0, half of 1.22, 0.61. Rayleigh himself already understood that this was an optimal solution, saying in the direction of original propagation, the secondary vibrations are all in the same phase, and hence the intensity is great as possible. There is a beautiful literature on prolate spheroidal wave functions. And so another version of optimization problem that the Airy pattern maximizes has to do with maximally localized waves with localization measured as some variance of the wave pattern subject to intensity. For a few reasons that I won't go into great depth here, these type of techniques are hard to translate to full vector spherical waves, to real apertures that one might have access to in experiments, and particularly to complex media. And so I'm not going to talk more about that today. There are a lot of interesting parallel results in that literature, especially in one dimension. You can also work out, away from the Praxial limit, what is the largest intensity that one can produce at the origin. Two interesting cases might be if you have access to an aperture of 2 pi, so you're coming from the hemisphere and trying to focus light to a point with band-limited waves, or maybe you have access to the full 4 pi aperture and you send in light. In both cases, you can write down the electric field in some basis. In the 2 pi case, often you might do this in plane waves. There's a polarization vector for every plane wave, and maybe you get to specify these coefficients subject to a suitable normalization. If I evaluate the electric field at the origin, again, it's just going to be an inner product of these coefficients against a very simple constant, and you can immediately read off what the optimal set of plane wave coefficients should be, and you end up with this expression here. When you go to 4 pi aperture, the more natural basis is vector spherical waves. In that case, it's remarkably simple. If you align your polarizations and your origin correctly, there's only one vector spherical wave that has any amplitude in the desired polarization at the origin. So the optimal thing to do is just excite that vector spherical wave. This was worked out by Shepard in '94, and you get an intensity that looks like this. One thing you might immediately notice is there's some different signs here. This is maybe not entirely understood by everyone. Aspects of it are known. When you excite waves from 2 pi aperture and you try to focus light to a point, you have to break the symmetry to maximize the polarization in one direction. And so what happens as you excite these plane waves from all directions is you start forming a donut beam for the polarization in plane. And what also happens is out pops some electric field polarization in the perpendicular direction that you can't get rid of. And you add those two intensities together, and you get this one. When you have access to 4 pi aperture, you can create the opposite polarization, interfere and destroy that out of plane polarization, and in fact get a tighter field distribution. So I just want to say 3 quick things about this free space diffraction. The first is that I, at least, was surprised at how much the full width half max and first 0 differ in these 3 simple limits. The classic 0.61 number goes all the way up to 0.77 in the 2 pi aperture case and down to 0.44 in the 4 pi aperture case. Same thing happens to the full width half max. The second point is that how you actually normalize these coefficients does matter. The one I showed before was normalizing the sum of the squares of the coefficients. But notice if I have plane waves coming in this direction, they might have powers that effectively cancel each other. It may take less power to send in plane waves from the side. And so you might imagine what we really want to do is what the experimentalists do is measure how much power we're supplying And it can lead to very different coefficients of the plane waves depending how you normalize. The fields look quite similar. The full width half maxes look quite similar. But you get very different coefficient normalizations. And a third point is that if you actually ask what the intensity is at the origin, you have to divide it by the normalization, which would be the incoming power that you supply. In the 4 pi case, Shepard and Larkin actually found a factor here that would be 4. This calculation was redone a couple years ago by Javier Garcia de Abajo, one of my favorite theorists. He said, no, it's 2. Shepard had done a vector spherical wave calculation. The wave comes in. We just calculated the power relative to the incoming spherical wave. Garcia de Abajo was interested in coupling to plasmons. He sort of did this on the way to that problem. And he redid the problem with plane waves coming from both sides and said, no, the correct number is 2. And Shepard sort of missed this interference with electric and magnetic effects. In about 15 minutes, I'll try to convince you the only sensible number here is infinity. What about space and time? I'll just do this briefly. But suppose you want to send in a pulse, and your goal is not just to maximize the field intensity at x equals 0 and y equals 0 and z equals 0, but also t equals 0. So then now you have access to plane waves, e to the I kx minus omega t. Let's take it one-dimensional in space. So I have some parallel wave number I can control. I have a frequency omega that I can control just for scalar waves in 1D. And I get to control the coefficients within some band limit. You can work through exactly the same thing. The optimal coefficients are 1 over the accessible waves. And what that produces is a pulse that sort of comes in and nicely hits a peak at x equals 0 and t equals 0 and then falls away. What's the full width half max? Actually, it's different when you do things in space-time than just in space. And the reason for this is exactly shown in this diagram. You have these pulses coming in. They localize, and then they go back out. These types of field patterns have been very beautifully seen in experiments. Here's a very nice paper from Professor Fort, where they see water waves going outwards and then refocusing in time. But I haven't seen very clear and good characterizations of these exact fields. And in fact, if you zero in at time t equals 0 and say, how localized is this field in space, it's significantly less localized than the fields we just looked at in the monochromatic case. So in the monochromatic case with an area-like pattern, you get the red electric field here. When I have a pulse that's optimized to concentrate in both space and time, when I look at t equals 0, the pulse is broader than it was just in space. And this effect is more dramatic in 3 dimensions. You send in vector spherical waves from all 3 dimensions. I have sort of a not great visual in the plane of the z-pointing electric field for such a pulse that comes in. But if we just pause at t equals 0, it looks like we have a nice focus spot in the xy plane. But if we dig into that, again, you see that these localized pulses maximized for space and time are significantly broader than those just in space. The reason for that, which is a little bit strange, maybe, space and time are not conjugate variables. There's no uncertainty relation, or if I concentrate in space, I can't concentrate in time. But causality says that all of propagation must occur within the light cone. And so what that means is that when I choose the optimal set of coefficients for my wave numbers and frequencies, I have to satisfy not only some limit on my temporal frequency, but then all the wave numbers for these to be propagating waves have to change as a function of frequency, their upper limit. And so if I want to localize in time, I can't just use my largest temporal frequency. I have to use the full range of temporal frequencies to localize in time. But if I'm using small temporal frequencies, those only have small wave numbers, which are very wide. And so that contributes to this broadening in space. Why talk about the diffraction limit in the first place? We all know that we can beat the diffraction limit. There are beautiful ensemble techniques that go in the near field and have resolutions of 10 nanometers. Famously, the Nobel Prize winning work says that you can shine almost 800 nanometer light on fluorescent objects, and you can get resolutions of something like 20 or 50 nanometers. And then even more important than the Nobel Prize winning work is that we can do photolithography with minimum feature sizes of something like 5 nanometers with light that might be 193 nanometers. Of course, none of these have anything to do with actually taking far field waves and focusing them more tightly. In this case, you're using prior information about sparsity that you know. There's a limit to the number of things that might be fluorescing at a time. In the near field, we're just accessing high wave number evanescent waves. And in photolithography, the light may be linear, but the material resist can be nonlinear. There are multiple exposure techniques that one can use, and so forth. Now, that's not what Nikolai Giladev was talking about when he wrote this commentary. He actually was talking about focusing far-field waves down tighter than the diffraction limit. And in particular, he was referring to a phenomenon called super oscillations, where you could take the normal array pattern and ostensibly bring its zeros closer and closer to the origin. This is, again, a topic that has a long history, going back to Tiraldo de Francia, at least, who noticed that if you take Airy's circular aperture and then you just block a lot of the center and create a ring, that's already a recipe for taking the zeros and bringing them in. You'd lose intensity, but you could bring the zeros in. Michael Berry has done a lot of very important work on this, and there's a lot of signal processing literature on creating these kinds of super oscillatory functions. I would say metasurfaces have suggested that it should be readily achievable to create super oscillations because you have a lot of control over incoming wave fields and the outgoing wavefronts that you produce. But I have not seen a good characterization of, as you make that distance smaller and smaller, as you bring these spots in, how much energy penalty do you really have to pay? There are non-computational bounds. We'll show that they're a little bit loose. And in fact, I think there may be some trepidation in even talking about super oscillations, because there have been suggestions that there might be exponential penalties to achieving super oscillatory waves. All right, so let's write this as a Rayleigh quotient optimization problem. No matter what type of excitation you might have to try to create the super oscillatory beam, what you can always do is put an aperture in front of it and say whatever fields are flowing through, they're creating effective currents by the equivalence principle. Those currents are radiating in free space. And so to understand what is the best super oscillatory field I can create, you might just ask, what is the best distribution of currents on some aperture that I'm given to create a focus at the center and maybe a zero field on a ring of radius d around the center. And this is the equivalence principle currents that one would create. Those currents are radiating in free space. And so the field at the focal point is given by a convolution of the free space Green's function with these currents. And if we write this in sort of a discrete matrix vector notation, gamma is a big matrix, C is a vector. And so the optimization problem would be something like maximize the intensity at 0, subject to normalization, with the one additional constraint that now my fields on this ring should also be 0. And so how to write this? You can define one operator that takes you from your entire aperture just to the point that is the origin. Let's call that gamma 0. And so if I have some number of aperture points n sub a, this is a vector that would be size 3 for 3 polarizations at the origin by 2 times na. I can define a second Green's function operator, this time taking me from the aperture to this ring. This will be the number of points on the contour C multiplied by 3 polarizations times number of aperture points times 2 transverse current polarizations. And so my optimization problem becomes maximizing a Rayleigh quotient subject to the usual normalization plus this extra condition that the fields on the contour must be 0. This is where the projection trick is very useful. If I need the fields on the contour to be 0, I can just take my currents and project out of any currents that produce non-zero fields on the contour. And so the first trick you can do is take that projection matrix, subtract it from the identity. This is now the projector out of any fields that produce, any currents that produce fields on the ring. Then I can remove that constraint. It just looks like a normal Rayleigh quotient problem. There's polarization I have to deal with. The way to resolve that is just pick an arbitrary polarization that you want to maximize, and then you just try different ones. At worst, you typically do 3 calculations. So I pick a polarization mu. I project the field onto that polarization. What happens is you get a rank 1 optimization problem. You can immediately write down an answer. It looks a little abstract, but what this tells you is you can pick any aperture you want. And fields, these are simple matrices you can calculate, and you can computationally produce a bound. Now, how much energy do we have to pay? There's one more trick you can do, which is that instead of forcing the field to be 0 at every point on this contour, as long as the contour is really small, you can actually just do a Fourier decomposition on the circle. Just keep the lowest order mode. So you can imagine you're coherently just forcing the average of the fields on the contour to be 0. And if you do that, you can actually work out all these Green's functions analytically, and you find a bound that scales like d to the fourth. So d is the size of the superoscillatory region you're looking for. The penalty you must pay in intensity scales as d to the fourth. And we can get all the right coefficients out front. If we plot the corresponding bounds, we get this blue line here. So if you start from the Airy pattern and go to smaller and smaller spots, this is the bound on how much energy or intensity you can get at the origin. And there have been lots of different proposals in the literature, but you'll see that there's actually pretty big gaps. This is something like a 10x gap from the bounds. One thing we also did, this is 3-dimensional. In 2 dimensions, we just did prototype inverse designs, and we found that we could hit the bounds at essentially going from 0.1 all the way up to 1, at least in 2 dimensions, using inverse design metasurfaces. So we think these bounds should be achievable.
Can you comment on it not being exponential?
Yes. 1 second.
Okay.
All right. So why d to the fourth? So first of all, we just worked this out. One interesting fact about the d to the fourth is that it's a little bit dimension independent. I can pick 2 points around the origin, force them to 0, it's d to the fourth. I can pick a ring, I get d to the fourth. I can pick a sphere. I can force the fields to be 0 on a sphere of radius d around the origin. Again, it's d to the fourth. And we just sort of worked all these out one by hand. Recently, I've realized there's a very nice scaling law approach to this, which is that, well, let me explain in a second. I don't want to give away the next part of the talk. There's a very nice way to understand in terms of dipoles and quadrupoles and things like this why it's d to the fourth. Why is it not exponential? So Michael Berry said you get this exponential energy cost. He was explicitly constructing superoscillatory functions. But the functions he created, as the spot size came in, he was bringing extra spots with them. So it was not just one pair of superoscillatory spots. It was a family of superoscillatory spots that were getting closer and closer. And what we think is that 1 point, if you want 1 point to be 0, you pay d squared. 2 points is d to the fourth. 4 points is d to the eighth, and so on. And so if you have this family that keeps bringing in more points, it's faster than any polynomial. It's exponential. The David Miller exponential, I don't want to go into the details of that. I'll just say he's effectively answering a different question that is not this question. So everybody's correct for the question that they're asking. All right, my favorite part of the d to the fourth is this. This looks very abstract. If you sit and stare at this for long enough, you can realize that it's actually giving you a simple physical solution for how to construct these superoscillatory functions. And what it's saying is that if you want to start here with currents and produce the superoscillatory field here, what you should do is start here, put a dipole there, let it radiate to your aperture. Then you put a second ring of dipoles here. You let those radiate to your aperture. The currents you take here should be the conjugates of the first field that you measured minus any contribution to the first field that overlaps with the second field. So you need to project out of the second field that's emanating outwards, conjugate, and the resulting currents are guaranteed to produce 0 field here because they have no overlap with the conjugate of the field that was radiated from the contour. But because they were generated by the field from here, they're also the currents that maximize the intensity here. So you start with dipoles here, here. You let them radiate. You conjugate. That produces exactly the maximum field at a point with 0 field on the contour. And it's guaranteed to reach the bounds. Now, all right, I said this is by reciprocity. Hopefully you heard me talk about phase conjugation. Do I really mean time reversal? Which brings me to my next topic, which is focusing in and through complex media. And again, there's so much wonderful work that's been done in this area, in particular by members of this collaboration. One of the application areas for focusing on complex media is imaging. And one of the ideas, which will be the inspiration for the setup I'll talk about today, are sort of guide star-based imaging techniques where you put a guide star in some complex tissue or something, you let it radiate outward, you measure fields, you time reverse them, and you send them back in. So we want to ask again, in what sense is this type of setup optimal, like in the free space case? So I want to deal with this toy problem throughout the next third of the talk. I have a point source like a guide star. It radiates in a complex environment. I can have arbitrary scatterers of any size, arbitrary materials up to a point. let them radiate outward. I measure the fields on some bounding surface, conjugate them, and I send them back in. So if we're talking about time reversal, let's talk about symmetries. I think the discussion of time reversal invariance is sometimes a little less clear than that for losslessness and reciprocity. The first thing you have to do in any of these scenarios is write down good notation. That's half the battle. So here's Maxwell's equations. And if you combine, create a 6-vector with E and IH, and then have epsilon mu here, and then your current sources put an I in front of the electric currents and a negative sign in front of the magnetic currents, it gets rid of all the annoying negative ones in all of these various symmetry conditions. And to simplify, if you have a material that has a Hermitian susceptibility tensor, generalized susceptibility tensor, and your Maxwell operator is Hermitian, that corresponds to losslessness. We know this is like a closed or periodic system. A reciprocity is the transpose symmetry of the susceptibility, and that's more general. You don't need a closed cavity. You can have open boundary conditions, and in that case, you end up with a symmetric scattering matrix and a symmetric Green's function. So time reversal invariance we know has to do with conjugate symmetry, and there's a simple relation for the scattering matrix. And you're very tempted to just say, well, all right, if I have a time reversal invariant material, then maybe I have a time reversal invariant Maxwell operator, and maybe I just take my field and I conjugate it. Let me emphasize, at the macroscopic scale, these are 3 independent symmetries. I can have all 3. I can have just one of the 3. I can be time reversal invariant without being lossless or reciprocal. I can be reciprocal without those 2. I can be lossless without these 2. Independent, I could also have none of the above. So let me give you the answer, and then I'll back up and explain it. There is a beautiful result. This might be my favorite result in the entire field, which says if I put a little source S sub 0 in a complex medium, I let it radiate outwards, and then I take the time reverse phase conjugate fields, send them back inwards. The field that is produced inside my medium, psi, is a convolution of the conjugate of that original source with the Green's function of my system, but not just the Green's function, only the imaginary part of the Green's function of my system. And that's a beautiful quantity. This is the quantity that arises in any power calculation. This is the non-singular, non-divergent part of the Green's function. It pulls out the singularity. And this explains, people think a lot about when I do this time reversal, do I get a diffraction limited spot? Do I get perfect focusing? What happens? Here you can see immediately I've removed the divergence. There is no singularity. And it's a very general expression. But why isn't this just the conjugate of my original field? I took my field, let it radiate outwards. Why don't I just get the conjugate when I do time reversal? It's well understood. The answer to this is well understood. I'm just going to frame it in my own language. So if I have currents that produce outgoing fields, proper time reversal would be reversing the outgoing fields and time reversing the currents. So I had an original current. I have fields that are going outwards. I time reverse these. I also just need to time reverse this field. This gets a little bit subtle in the time domain, but in the frequency domain, this is very clear. These are just steady state processes. I have a steady state current and steady state outgoing fields. The time reverse needs to be the steady state incoming fields and the steady state current. In the typical setup we care about, like in a lab where you measure at the exterior and then you send light back in, you have removed the field in the center. And so you actually are not doing just the time reversal symmetric partner of the original scenario. You're doing the time reversal symmetric partner minus the contributions from whatever original currents you had. So it's sort of a partial time reversal scenario. The derivation of this result requires a lot of dexterity with Green's functions. And I love Green's functions, but even I had to stare at this for a while to try to understand what was going on. And there are also 2 things that I would like to do to try to generalize this a little bit. One is that reciprocity is used in this derivation. At some point, you use the transpose symmetry of the Green's function. But reciprocity and time reversal invariance are different symmetries, and let's try to keep reciprocity out of this. Also, if you take a Green's function approach to these kinds of problems, I think you've sort of immediately given up on the nonlinear cases because Green's functions need the superposition property. So let's try another way of analyzing this. Obviously, the difficulty with the conjugate symmetry of M, just like the Hermitian symmetry and the reciprocal symmetry of M, has to do with the open boundary conditions. One simple way of dealing with open boundary conditions is to put a perfectly matched layer. And what happens is then in your Maxwell tensor, you have some perfectly matched layer material that's doing the absorption of the outgoing waves for you. And so then you go to do time reversal. And not only do you have the time reverse of the original currents, but now you have the conjugate of the perfectly matched layer that's sort of spitting back fields for you. And you have these conjugates of the permittivities here. And it's not that simple to try to work out theoretical properties with the conjugate of a PML. And clearly, it's not true that m star equals m, because in this framing. There's an alternative framing, which can work as follows, is that instead of using a PML, let's take a surface outside all of the scatterers, and let's put currents on this surface. One might call them perfectly canceling currents, given by the electric field and the magnetic field, according to the surface equivalence principle, that null out the field everywhere to the exterior of this surface. So I put electric and magnetic currents down. That nulls out the exterior fields. Those go to 0 everywhere there. And what's nice about this is that then the perfectly matched layer is redundant. You don't need it. You could, in fact, replace it with a perfect conductor, perfect electric conductor, a perfect magnetic conductor. And so now the currents are doing the work of perfect absorption of the outgoing waves. This is not a useful computational principle. You need to know the fields ahead of time to figure out what these currents are. But it's a useful theoretical principle. And so the idea is you take the original problem with the original Maxwell operator that has these outgoing radiation conditions, you replace it with a perfect conductor, and you add a new source term on the right-hand side of Maxwell's equations, which are exactly these electric and magnetic sources. And so this problem is exactly equivalent to this one. But this now gives us hope, because maybe we can conjugate the perfect conducting operator. And indeed we can. Why do we call these perfectly canceling currents? If adding these currents produces 0 fields in the exterior, then by linearity, the original field produced psi in the interior and some psi exterior in the exterior. So the only thing adding these currents did is they nullified this. And so really what they're doing is they're producing just an outward going field that is exactly the negative of the original outward field. So you put these currents down, they just radiate outwards, but they radiate outwards exactly out of phase with the original outward going fields. All right, so now we can actually analyze this phase conjugate field process using perfectly canceling currents. So you start with your original problem. You put the perfectly canceling currents down, you put your perfect conductor down, you rewrite Maxwell's equations in this way. Then you just conjugate everywhere. So now I have the conjugate of my Maxwell perfect conductor operator, conjugate field, the conjugates of the sources on the right-hand side. And now the key idea is I can replace this by time reversal symmetry with the original one, as long as just the materials are time reversal symmetric. And so when I do that, I get back to my original perfect conductor Maxwell equation, these on the right-hand side. Nowhere in this process was the 0 field in the exterior modified. And so I can actually take that perfect conductor and replace it again with a normal outgoing boundary condition without changing the problem. And what that means is that I can then recover my Maxwell operator with outgoing boundary conditions with just these fields on the right-hand side and say that with a normal outgoing boundary condition, the conjugate of these sources produces exactly the conjugate of my field everywhere. And so I think this is sort of a nice, simple description of how to do time reversal symmetry in these open systems, is that you start with some set of localized sources. The conjugate is, you take the conjugate of the perfect canceling currents, the conjugate of the original fields, and that produces exactly the conjugate of your original field. Then it also becomes very easy to analyze sort of the experimentally relevant case if I just have these phase conjugate sources on the boundary, which are exactly the conjugates of these perfectly canceling currents. I want to know what field they produce everywhere to the interior. So that field is produced with normal Maxwell equations with these conjugate currents. That's exactly the full time reversal symmetric partner minus just the field produced by a conjugate source. And you can just do a very simple subtraction of the conjugate of the field minus the field produced by this conjugate source. And you recover exactly this simple imaginary part of a Green's function convolved with this source. And again, this is a known result, but a nice way, I think, of understanding it. Okay, is this field diffraction limited? Hopefully everybody here sort of nods yes, it's diffraction limited. There are a few ways to see this. One is that if you actually just look at the imaginary part of the Green's function, let's say in free space, the normal Green's function is the divergent Hankel function. The imaginary part is the non-divergent Bessel function, which is certainly a diffraction limited field. Why does this field have to be diffraction limited? Because you're coming from outside. This was my impression too, is that you're coming from far away. If I put fields on a boundary far away, I cannot get a subdiffraction limited beam in the interior. But this is not the reason. So if I imagine free space, if I take this bounding sphere and I take it all the way right next to a point source, and I follow exactly this procedure, I will get a field that has uniform intensity in the interior that has no divergence at all. You need the sink. And so let me explain this in two ways. One is, so in the process of time reversal, you have to conjugate the original fields and you conjugate the exterior fields. So if you conjugate everything at once, you get the conjugate of a divergent field is still divergent. That divergence never came from conjugating the exterior fields. It entirely came from conjugating the interior fields, which act exactly as this sink. Another way of understanding it is through the perfectly canceling currents. So in this setup, there are perfectly canceling currents to the exterior. They produce fields that only go outward. You can imagine there might be evanescent waves that go outward, and there are also propagating waves that go outward. When you do the phase conjugate, you flip the plane wave, the propagating plane waves, to go inward, but the evanescent waves just keep going outwards. And so the funny thing that actually happens is that if you take this boundary and you bring it into the center, it creates a uniform field in the interior and diverging fields right on the outside of the boundary due to the evanescent tail of these fields. But they don't create a focus at the center, because you have to have the time reversal of the original source to do that. All right. How large can this field be? There's another nice aspect of the fact that you have the imaginary part of the Green's function. If this guide star is just a point source, this is proportional to the local density of states. This has been pointed out certainly before. In a previous Simon's talk, I talked about a lot of work we've been doing on what are the upper limits to local density of states. And what we've seen is that as you take structures that come closer and closer to a point source, you can get a local density of states that scales in a limit like 1 over d squared. And so in fact, if you do this time reversal process with structures that are very close, you can certainly get below diffraction limited focusing because you now have a near field. The bound on how large that field can be as these structures come in scales like 1 over d squared. Maybe the more important question in my mind is this optimal with respect to maximizing the field strength at x0? So let's try to set up another Rayleigh quotient optimization problem. And the normalization here is the experimentalist does some amount of work to generate these currents. Let's set that amount of work to be 1 and maximize the field at the origin. So a quick detour on work done by currents. Suppose I just have a plane wave propagating in free space. The surface equivalence principle tells me that I can draw a bounding sphere anywhere for this plane wave. I can specify currents according to the normals on these boundaries that nullify the fields to the exterior and produce a field to the interior. These currents are doing no work. There's no radiation. And so this is an example of a non-radiating current distribution. If I ask in this simple setup, what is the field intensity? At this point, it's 1. How much power did I supply? 0. And so the answer to how much intensity I can get for a unit amount of power is infinity. Now you might say, okay, well, physically what's happening here? Physically, let's ignore the top and bottom boundaries. The left wall, those currents are producing a wave that's propagating to the right. The right wall is producing waves that also just go to the right, but with exactly the opposite phase. That field disappears to the right boundary. And so this boundary is actually absorbing the power that's being generated by this. So the total net power is 0, but that comes from power being generated here and being absorbed here. And so you might say, well, look, this is easy. Just look at the points that have positive power flow. Only count those, and don't worry about the points where you're absorbing. You know, in this case, the left boundary has positive power flow. The right is negative. The total is 0. But the problem is, even if I force the optimization to just have power that's non-negative at every single point, I can still get exactly these types of solutions. A simple example of this is with cylindrical waves. In the cylindrical wave case, now I have ingoing and outgoing cylindrical or spherical waves. And now at every point on this boundary, if I ask how much work is being done, the answer is 0. And so what's happened is you found a steady state solution where these currents are oscillating, and the fields that are being produced are being reabsorbed by those currents, which gives it the energy to then produce the next wavefront that's being generated. And so as far as I can tell, with monochromatic light, there is no way to regularize this problem in sort of a simple, elegant, theoretical way. The only real answers we have are, one, is to try to model in the physical experimental system how is power generated. Or two, you switch away from power normalizations and go to an amplitude normalizations. And this actually is the correct resolution of the discrepancy between Shepard and Garcia de Abajo, is that Shepard was doing the calculation in vector spherical waves. He was essentially assuming incoherence in the basis of vector spherical waves. Sorry if I pressed something that got the screen there. And Garcia de Abajo did plane waves, and he just separately calculated the powers coming from the left and the right and assumed no coherence between those two planes. And every different basis, if you just pick out and say this is the part that generates power and this is the part that absorbs power, and I'm going to ignore that, will give you a different answer. And so I don't think one is necessarily more correct than the other. You would have to probably try to match this to your experiments. This also connects with, if you think it's just the magnetic currents here that are producing this capability, there are also plenty of electric current only non-radiating distributions that will have this property. All right, so what's the optimal field? This becomes a rank 1 Rayleigh quotient optimization. I won't go through this in detail. I'll just say you have a source on your boundary. I want to maximize the field at the center. That's a Green's function. It's not the free space Green's function anymore. It's the Green's function of your particular system. You project into a specific polarization. It's exactly like the super oscillation problem. We don't have the annoying 0. The optimal currents, this is V times V dagger. The optimal currents are just V, so gamma dagger times phi. If we rewrite these, we can pull the conjugate out. We have this annoying Green's function that goes from the boundary to the origin, but it's the transpose of that. If we have a reciprocal medium, we can switch origin to boundary without the transpose. All right, is this exactly what we do in time reversal? Almost. So in time reversal, you're setting these conjugates of the perfectly canceling currents that are given by that expression here. If you work through the vector I just defined and you write out what are these optimal currents, it's a global phase times minus E conjugate and H conjugate. So it sort of looks a lot like the perfectly canceling currents, but it's not the same. They are the same in one limit, which is when you're far away from all scatterers. When you're far away from all scatterers, then all power is flowing perpendicular to the surface. The electric and magnetic fields are related, form a coordinate system with the normal vector. And in that case, these optimal currents are a global phase exactly times the perfect canceling currents. And so there's a nice discussion of some optimality, not in this language, but in this paper here. How large is the optimal field in general? It's just given by an integral along the boundary of the squares of the fields. This is also nice. You can imagine in the far zone, this is exactly proportional to the radiated power, which is exactly proportional to the local density of states, so everything's consistent. In this derivation, was the 4 pi solid angle necessary? No. I used a Green's function that was defined from my aperture to my point. Nominally, I made this the boundary of a volume. But if all my integrals had just had some finite-sized aperture, everything in the derivation would still work. Is time reversal invariance necessary? Actually, no. The medium need not be time reversal invariant for this to be the optimal set of currents. At no point on the previous slide, I pulled a conjugate out and then interpreted it. But nowhere here did I assume that there's any kind of conjugate symmetry in the materials themselves. And finally, is reciprocity necessary? Yes. It was necessary to take the Green's function from the boundary to the origin and flip it around to use reciprocity. And so I think what I'd say is this. What time reversal gives you is a very nice description of what are the fields that are produced when you take the time reverse currents on the boundary. But if the question you're asking is, suppose I have an aperture and I want to focus light. Should I put a dipole where I want to focus and measure the response out here to figure out what currents to do? Fundamentally, the process I'm doing there is I'm switching the source and receiver measurements. That is reciprocity. It's connected to time reversal invariance in some scenarios, but it's really a property of reciprocity that says this is the optimal procedure. And the optimal procedure is not exactly to do time reverse the fluxes. It's to conjugate the fields so that by reciprocity there's interference when they meet back at the focal point. All right, so this is just a summary of exactly what I said in words, that no matter what size aperture you have, if you want to focus back to a point, this is the recipe to do it. In the case where your aperture is 4 pi, you're doing measurements in the far zone, and your medium is time reversal invariance, then the procedure you should follow is exactly the time reversal invariance prescription, plus in that case you get to know the fields everywhere by the time reversal symmetry. Now, one phenomenon I've not seen is, can you create these super oscillations in complex media? Hopefully you can tell by this reciprocity prescription that the answer is yes. If I start with a complex happy face scattering refractive index profile, I have fields that go outward. I can put currents on the boundary, create perfectly canceling currents, and bring them back inwards. I create a nice diffraction limited spot at the center by following this procedure. If I want a super oscillatory field, it seems very difficult potentially in a complex medium to know how to construct these super oscillations. But what reciprocity tells us is just put point sources at exactly the locations where you want the field to be 0. Let those radiate outwards. Take that contribution out of the currents that you're exciting on the exterior. And then when I excite back in, I can get 0 field at any points that I desire. So I put 2 currents down. I let them radiate. I measure exactly the fields. And I get a little pinched feature right in the center. And if my original field is a nice diffraction limited spot, just by taking those points and making them closer and closer, the fields that are produced from the exterior have exactly this super oscillatory nature to them. There's an energy penalty, of course, as I create these super oscillatory fields. It turns out that energy penalty, by general principles, is exactly the same 1 over d to the 4th scaling as we saw in free space. All right, in space-time, I will just say you can use exactly the same principles. You want to be a little careful about how you use reciprocity in time. Often when people use reciprocity in time, they relate the retarded Green's function at one point in space-time to another one, to the advanced Green's function coming back. The problem here is if you want to use this prescription to focus light in time in a medium, you'd have to run it backwards in time or use time reversal invariance. If we want to avoid that and just use the principle of reciprocity, there's another version of the reciprocity principle in time invariant media called the convolutional reciprocity relation, which says, in fact, in time invariant media, if I have 2 sources that emanate at the same time, I can let them both propagate forward in time, and the retarded Green's functions will be transposed symmetric partners of each other without flipping the time variable. So I actually can run the simulation forward in time, measure the fields, and that tells me how to then create currents that maximally focus at a given time without doing any time reversal or back propagation. All right, in nonlinear media, I'll just make one point briefly on this. Let me maybe skip the symmetry. For those who are interested, I'd be happy to talk about it. What I think is really nice about this prescription is that I think it translates seamlessly to the nonlinear case. And the reason for that is that before this m is linear, I'm just going to say by fiat that I can just put a parentheses there and say this can be a nonlinear operator. The reason why this works, the only place this would be questionable is we used linearity to put these currents down before. But as long as the medium to the exterior is linear, all those currents are doing is they're just radiating outwards. They're not radiating inwards. And so if I have a nonlinear scattering profile to my field, and I just measure the fields on some boundary, I can still specify currents that exactly cancel those and have no interaction with the nonlinear medium to the interior. So we can still follow exactly the same procedure and start to understand what are the time reversal symmetries in the nonlinear medium case. I won't show, we have ongoing work in this regime. I'll just mention the one thing that does fail is we cannot take the experimentally available apparatus and rewrite it as a linear superposition of the time reversal partner minus this. But what we can say is we know exactly the fields in the perfect time reversal symmetric case with nonlinear media. And the question just becomes, when I remove the original source, how much does that change my nonlinear solution? And so that can give us a lot of clues in these nonlinear systems of when the change will be small, and the nonlinear case will be exactly like the linear one, and when the change might be enormous. It has to do with how much removing the interior source does. Of course, there are also issues with bistability and uniqueness that Mario has talked about very nicely in previous talks. But this gives us a nice framework for understanding multiphysics. And then briefly, let me end where I should have started. Do we even need to focus waves anymore? It used to be that with imaging, you wanted a lens to produce an image. Now you start with an input, you produce a speckle pattern, and you use deep learning, and you get your image. Do we need to focus light? There's a long history of computational imaging. What has become clear is that people now just model the system end to end. I have my photonics. They interact with the detectors. And then I have algorithms on the back end. And I can just optimize the entire system forward and backward. And Stephen gave a beautiful talk on this at Simon's a few years back, where they did exactly this end-to-end process. And they had a metasurface. And then they had detectors. And then they had back end to extract images from some set of objects. But there's a very strange result in Stephen's paper, which is that their imager formed images. What I mean by that is that the metasurface actually at the detectors was taking inputs that looked like A's and E's and C's and D's and forming exactly the A's and E's and C's and D's at the detectors. And this is very non-trivial for a metasurface. It is very difficult to focus broadband radiation down to a point and form an image, and yet their system was doing it anyway, even with the full computational apparatus of an algorithm at the back end. Why were they doing this? Fundamentally, it's because in most of these photonic systems, you have the photonic transform, and then you have detectors. And what those detectors do is they measure the intensity of the field that falls upon them. And that's very important, because we have a linear system, y equals some transfer function times x plus noise. But this transfer function has to be positive everywhere, right? The intensity incoherent transfer function. I won't go into details on this. I'll just say, so we've been analyzing through both a mutual information perspective and a Fisher information perspective how you maximize the amount of information that the photonic system produces at the detectors from the sources. And the assumption there is that the back end will be so good that it will extract any information that has made it to the detectors. Well, what became clear to us is that you can't do the normal thing of just having inputs that create outputs that are large in some orthogonal vector space, because if I have orthogonal vectors that are negative or complex, the detectors project all of that just back into the first orthant. And so huge amounts of information are lost if what the imager is doing is not already creating orthogonal vectors in the first orthant itself. And so in fact, the optimal thing you always want to do if you have these intensity measurements is have measurement vectors that look exactly like a permutation matrix that are zeros everywhere except for a single one. And it's the idea that it's easy to create basis functions when you have coherence out of any oscillatory function. As soon as you go to intensities, the only orthogonal basis function, in essence, are the delta functions. All right, I won't prove this. I'll just say that we prove this for both things. We ran a variety of simulations of meta-imagers that might take sources to receivers. We found exactly this permutation matrix behavior, that what the optimal designs did is they took sources and they produced focused light like funnels at different receiver points, whereas when we allowed amplitude and phase measurements, there was much more measurement diversity, so it's the intensity that really mattered here. If you were interested not in point-to-point, but like Hermite-Gauss incoherent excitations to then extract information in a sensing perspective, exactly the same type of phenomenon behavior occurred. The Hermite-Gauss modes got focused down to single points by a complex scattering structure. So exactly this permutation matrix type of response occurred. This also acts as a way to do the optimization itself without including the back-end algorithms inside of it. It performs essentially equally well. This has also been very useful for other projects we have with doing multifunctional grading couplers and things like that. And so finally, I'll mention, I think one reason this is useful, and this is a good place to close, is that by understanding what the limitations are in the photonic systems, you can start to understand fundamental limits to how good these systems can be. One thing that was really clever in their setup is that they had the metasurface, and then the measurements were done on an aperture that was something like 10x bigger than the original one. And why that's useful is that metasurfaces can't focus all this broadband light to a single position. And so by allowing the screen to be bigger, it could send the blue light to one region and the red light to another region and the green light to another region. And by understanding things like this generalized focusing principle, that permutation matrices are optimal, you can start to figure out the physics of what makes the optimal end-to-end imaging system, even without getting into the nitty-gritty of how the backend works, what neural networks can do, and things like that. All right. With that, I will thank you. I apologize for going a bit long. I'd be happy to take 1 or 2 questions.